Alrighty, okay, so another improvement that I could make was the second improvement is that to dynamically size the number of buckets or let the caller specify the number of buckets each hash map specify the number of buckets for each hash map created. Okay, dynamically size the number of buckets. Okay, how can I go about that? Right, so we will make some changes here. Right, default key compare, node compare. Okay, so create. Okay, so we are creating this default number of buckets, right? I think I'll just overthink it. You can use better two of them. Okay, so this is let me go original code improvement regarding dynamic uh, dynamic growth of the bucket, right? Okay. So dynamically, right? Okay, so okay, see, currently what we do is we go hash map find bucket, right? Okay. So we hash it with the default number of buckets. We hash it with the default number of buckets, and then we get the bucket number. Okay, but then but see, it is dynamic, right? Growth, hence I'm going to define a bucket with size 1 right now, which will increase as it goes on, right? Dynamically increase the bucket size, okay, for the hash, but hash would be different every time. I think I should, okay, you can dynamically size the number of bucket or let the caller specify the number of each buckets. Okay, see, say I have to dynamically make it grow. Let's think about it. Right, okay. So I have this, right. Okay, so say I generate a hash, right. Okay. Say one hash table. Okay, see, the thing is with mod, right? With mod, The that thing is that for all the numbers bigger, say I have a size of, say I have an initial size of 10, right? Initially I have a size of 10. Okay, then say 0 0 mod c modulus 10 equals to any number bigger than this, right? Any number bigger than this would have the same property, right? 1 mod 11 and 1 mod 10 would be same, however the difference would be 10 mod 10 would be 0, 10 mod 11 would be 10. That is all the difference, right? But uh, so yeah, okay, but if it is already 0, right, and I indeed do get a 10, okay, yeah, then that would not make sense, right? Because if, like, say if the value of hash was 11 and I mod it with 10, I get 1. Now with the new hash I go 11, then I mod it with 11, I will get 0. But since our hashing has changed, dynamically size the you can dynamically size the number of buckets. Okay, maybe I would have to put the easier answer. See, so this is in bucket 0 and this is in bucket 1, so no way am I going to find it after the size has changed if I'm depending on this, right? Okay, so for now, improvement, I go improvement, letting the user decide the buckets in the hash map, right? So you can go here, hash map create, size t, size, simply size t, buckets, buckets, okay. As part of improvement, lets the user specifically, okay, so original code, okay. User specifically decide the size of the buckets. Okay, with size bucket, so let's change. Okay, why am I serious? Just go there. There's hash map create. Let me add a size g buckets. Then there we are. Okay, so improvement. So I go map buckets equals the array create size of the array and then buckets. Okay, there we go. Then here uh, default hash. This is original code. This is improvement. Uh, Hashing with the new size of the buckets. So I'll simply go int bucket n equals hash mod the array count, and I have map buckets. Okay, so after these calls, let me go where is the tests. Okay, sorry, test slash, there's my bad, there we go, test. Okay, but I didn't really, okay, yeah, right, okay. So then I just update to is good. Get set, create, okay. Original code, improvement, that's the user, decide the number of buckets. Okay, so I go map equals hash map create default, and then I can pass like 10. Okay. Hash map destroy works the same, and then okay, so I just want to make sure that everything works. Okay, yep, so everything is right, nothing is broken. Alright, so that improvement is done. Hashmap.h. Okay. Anything all it though? Done. Let's the user decide the default number of buckets. Okay, you can use a better default hash. There are tons of, okay, I want to go and search. Okay, let me go search buckets and hash maps. What exactly is bucket in hash map? Okay, simply, okay. On an interview I was asked what exactly is a bucket in hash map, whether it is an array or an array list or what. I got confused. I know hash maps are backed by arrays, so I say bucket is an array with a capacity of 60 and starts storing hash codes into which linked lists have their start pointers. I know a hash map internally works, but you know what exactly is bucket? Okay. No, a bucket is each element in array you are referring to. Okay, in earlier, right. Okay, what are hash buckets? Right, okay, these are buckets. Okay. So, how to dynamically increase the number of buckets in hash map. Why hash map resize? Okay, currently hash map in Java resizes total number of elements inserted greater than load factor when, so it doubles the table and rehashes. Okay, so I would have to rehash all the values, key values. But suppose hash code in key class is hard coded to say, let's say 1. So every time element will be inserted at index 1 in the linked list manner. Okay, hash map has some code that prompts. Okay, hash map has some code that attempts to improve bad hash code implementations, but it can do nothing to improve a terrible hash code implementation that always returns the same value. Okay, such a hash code will give bad performance regardless of whether or not you resize the hash map. Therefore, such bad usage of hash map doesn't justify adding special logic as suggested. The assumption on the hash code implementation of the key is that it will distribute the keys as closely to uniformly as possible among the hash map bins. Right. Therefore, the average number of entries in a bucket, which is the total number of entries divided by the number of. Okay. Therefore, the average number of entries in a bucket, which is the total number of entries divided by the number of buckets, should give a good estimate on when the hash map should be resized, and the size of individual buckets doesn't need to be checked. Okay, so this is total number of entries divided by number of buckets. Okay, this. Okay, so this is the condition of bucket. Okay, some points regarding dynamically sizing the hash map. Okay, so some points regarding dynamically. Just go. So, average number of entries in a bucket, which is the total number of entries divided by the number of buckets, should give a good estimate. Individual doesn't need to be checked. Right. Of entries. It should be resized and the individual buckets doesn't need to be checked. Okay. So, imagine a hash map with size 12 and 9 items in it. Okay. Let's say that by coincidence, hash code only returns multiples of 3. It's still a flawed hash code, but it's not a contrived edge case such as constant code of hash 1. This means that in case only 4 buckets would be filled with 1 or 2 elements. With our approach, this hash map would never get resized. The collision list would grow forever and the performance would suffer. However, if you resize it based on total size, the load factor of 75%, that would be adding 10th element. You'd end up with a hash map with 24 buckets, 8 of which will be filled. Growing based on total size keeps the collision list at a reasonable size. With realistic imperfect hash function, because it's reasonable to expect every hash function to at least make a best attempt to distribute hash, meaning that growing a hash map will lead to more buckets than previously, even if. Okay, so also when you change the size of the hash map, you have to also update their positions based. So when you change the size of the hash map, you have to also update their positions based on the new size of the buckets. Resize the positions of elements based on the new size of the buckets. Okay, if hash code always returns same value, it is bad implementation, no logic of supporting what should not be done. Okay, 2 hash code may not be constant function. Hash map has no way to know if the hash function is of type constant or not. If so, it is wise to resize hash map, as in case suddenly hash code becomes non-constant function, then resizing may result in a better distribution. Okay. How does right? Okay. So in Java, a hash map increases its size through a process called rehashing when the number of entries exceed a certain threshold defined by the load factor. Okay, so there is a load factor, right? So here's how it works. Initial capacity. When a hash map is created, it has an initial capacity, default is 16, and a load factor, default is 0.75. The load factor determines when to resize the map. Okay, then threshold. The threshold for resizing is calculated as capacity. So the threshold for resizing is calculated as capacity times load factor. For example, with an initial capacity of 16 and a load factor of 0.75, the threshold would be 12. Okay, inserting entries. When you add entries to the hash map, it checks if the current size exceeds the threshold. If it does, hash map needs to be resized. Okay. Resizing. Doubling the capacity. The capacity of the hash map is typically doubled from and then rehashing. All existing entries are rehashed to new table. This is necessary because the hash function may distribute the entries differently in new larger array. Okay, performance consideration. So rehashing means we create a new hash map and then all the new entries are added from there, right? Okay, all existing entries are rehashed to new table. This is necessary because the right, okay, I get it. You have to also update their position, the element space, and this process is called rehashing, since the new since okay, performance resizing is an expensive operation because it involves creating a new array and rehashing all existing entries. Okay, therefore, it's generally a good idea to set an initial capacity that is close to the expected number of entries to minimize the need for resizing. Okay. Then we have there's a brief number of okay there's a brief example there's a brief example of how you might create a hash map with an initial capacity and load factor. Okay. Okay, when I add, right, bucket, okay. Okay, hash map set. Okay, so we go, bucket is this, default number of buckets. Ooh. We are creating each bucket of size 100. Default number of buckets. Dear, a bucket Damn. Default number of buckets 100. Now set it up. We are giving it a initial value of 300. Okay, so I'll have 100 elements can fit within this, right? Okay, so a good thing was that the average number of entries in a bucket, which is the total number of entries divided by the number of buckets, should give a good estimate on when the hash map should be resized, and the size of individual buckets doesn't need to be checked. Okay, how can I get the total number of? Okay, so that is the load factor, right? Okay, resizing is an expensive operation because it involves creating a new array and rehashing all existing entries. Okay, so I have to create a new. Therefore, it's generally a good idea to set an initial capacity that is close to the expected number of entries to minimize the need for resizing. Alright, here's a brief example of how you might create a hash map with an initial capacity and a load factor. This creates so two factors that affect the performance of hash map are initial capacity and load factor. The size of the hash map represents the entries. Okay, this value is updated each time an entry is added or removed. Do I have an entry? No, right, but I can simply no, but it this won't give me. Okay, so I can maintain a size, right? Maintain a size. Okay, I want the hash map to grow dynamically, right? Okay, you can use a better default hash, but I want to make it grow dynamically. Okay, I can start with a default value, right? And then I can resize. I can just okay, I'll double it. Okay, so this and okay, I'm just improvement 2.1 2.1 done. Let's the user decide the default number of buckets, and I should also update this. We do have a map, right? Yep. Okay. So array count map buckets. Let me make okay, there was okay, then yep, right, works absolutely fine. Alright, so fixed number of, I'm adding 3 value, and I have a bucket size of 10. Okay, so here the total okay, so I can say an improvement improvement is improvement for dynamic. Okay, so for okay, we have for improvement for dynamic. Let me see. What for dynamic growth, right? We will maintain two more variables. We will maintain two more variables. Uh, Size for storing the total for size to know the number of currently added elements, right? And second is I have learned is load factor to decide the condition for resizing elements. Load factor decide size and sorry, what was that? Double load factor, right? So updated at every entry. Okay, so let me read another. The capacity is the number of buckets in the hash table, and the initial capacity is simply the capacity at the time the hash table is created. The load factor is a measure of how full the hash table is allowed to get before its capacity is automatically increased. Okay. Then when how many buckets, right? Initial capacity equals 16, and the load factor determines when to resize map. Threshold is the threshold for resizing is calculated as capacity times load factor. For example, with an initial capacity of 16, the threshold would be 12. But 12 what? Inserting entries. When you add entries to hash map, it checks its current size. If the current size exceeds the threshold, if it does, if its current size, okay, threshold, so capacity time load factor. Yeah, I think I should look into the book. Here, data structure and algorithms books. Say what this guy have to say about algorithm dynamic data structures is the hashing and strings. Uh-uh. Sorting, keep data structure and weighted graphical algorithm dynamic data structures is the dictionaries and how can you okay dictionaries. So I have a set of n records each identified by one or more key field program description. Build and maintain a data structure to efficiently locate, insert, delete, and record associated with any query key Q. Okay. The abstract the abstract data type dictionary is one of the most important structures in computer science. Dozens of data structures have been proposed for implementing dictionaries, including hash tables, skip lists, balanced and unbalanced binary search trees. This means that choosing the best one can be tricky. It can significantly impact performance. However, in practice, it is more important to avoid using a bad data structure than to identify the single best option available. Okay. An essential piece of advice is to carefully isolate the implementation of dictionary data structure from its interface. Use explicit, okay, essential implementation of dictionary. Use explicit calls to methods or subroutines that initialize, search, and modify the data structure rather than embedding them within the code. Okay. This leads to a much cleaner program, but it also makes it easy to experiment with different implementation to see how they perform. Do not obsess about the procedure call overhead inherent in such abstraction. If your application is so time critical that such overhead can impact performance, then it is even more essential that you be able to identify the right dictionary implementation. Okay. In choosing the right data structure for your dictionary, ask yourself the following question: how many items will you have in your data structure? Will you know this number in advance? Are you looking at a problem small enough that is simple? That a single data structure will suffice, or one so large that we one so large that we must worry about running out of memory or virtual memory performance. Okay. Do you know the relative frequencies of insert, delete, and search operations? Static data structures like sorted arrays suffice in application where there are no modification to the data structure after it is first constructed. Semi-dynamic data structures which support insertion but not deletion can have significantly simpler implementation than fully dynamic ones. Okay. Can we assume that the excess can we assume that the access pattern for keys will be uniform and random? Can we assume that the access pattern such queries exhibit a skewed access distribution in many applications, meaning certain elements are much more popular than others. Further, queries often have a sense of temporal locality, meaning elements are likely to be repeatedly accessed in clusters instead of at fairly irregular intervals. Certain data structures such as play tree can take advantage of a skewed and structured universe. Is it critical that that individual operations be fast, or only that the total amount of work done over the entire program be minimized? When response time is critical, such as in a program controlling a heart-lung machine, you can't wait too long between steps. When you have a program that is doing a lot of queries over the database, such as identifying all criminals who happen to be politicians, it is not as critical that you pick out any particular congressman quickly as it is that you get them all within the minimum total effort. Okay, an object-oriented generation has emerged as no likely to write a class container class then fix the engine in the car. This is good. Default containers should do just fine for most applications. Still, it is good sometimes to know that you have what you have under the hood. Okay, unsorted linked lists or arrays. For small data sets, an unsorted array is probably the easiest data structure to maintain. Linked structures can have terrible cache performance compared with sleek, compact arrays. However, once your dictionary becomes larger than say 50 to 100, The linear search time will kill you for either list or arrays. Okay. Details of elementary dictionary implementation appear here. What page am I on? A particularly interesting and useful variant is self-organizing list. Whenever a key is accessed or inserted, we always move it to the head of the list. Thus, if the key is accessed again sometime in the near future, it will be near the front and so requires only a short search to find. Nice. Most applications exhibit both uneven access frequencies and locality to reference. So the average time for a successful search in a self-organizing list is typically much better than in a sorted or okay. Of course, self-organizing data structures can be built from arrays as well as linked lists and trees. Okay, sorted linked list or arrays. Maintaining a sorted linked list is usually not worth the effort unless you are trying to eliminate duplicates. Since we cannot perform binary search in such a data structure, a sorted array will be appropriate if and only if there are not many insertions or deletions. Hash tables. For applications involving a moderate to large number of keys, a hash table is probably the right way to go. We use a function, right? I'm learning about hashing and string, data structures and dictionaries. Set data structure, numerical problem solving, linear equation, bandwidth, random number constraint, combinational problem, graph problems. Okay, for application 100 to 10 million, a hash table is probably the right way to go. We use a function that maps keys, be the string numbers or whatever, to integers between 0 and m minus 1. We maintain an array of m buckets, each typically implemented using an unsorted linked list. Right. Okay. The hash function immediately identifies which bucket contains a given key. If we use a hash function that spreads the keys out nicely and a sufficiently large hash table, each bucket should contain very few elements, thus making linear searches acceptable. Insertion and deletion from a hash table reduce to insertion and deletion from bucket list. Provides more detailed discussion of hashing and its applications. So, a well-tuned hash table will outperform a sorted array in most applications. However, several design decisions go into creating a well-tuned hash table. How do I deal with collisions? Open addressing can lead to more concise table with better cache performance than bucketing. Open addressing, okay. But performance will be more brittle as the load factor, the ratio of occupancy to capacity of the hash table starts to get high. Okay, ratio of occupancy to the capacity. Okay, how big should the table be? With bucketing m should be about the same as the maximum number of bucket you expect to put in the table. With open addressing, make it say 30% larger or more. But open addressing, selecting m to be a prime number minimizes the dangers of a bad hash function. Okay, this I didn't know. Selecting m to be a prime number minimizes the dangers of a bad hash function. What hash function should I use? For strings, something like this. Should work where alpha is the size of the alphabet and char x is the function that maps each character x to its ASCII character code. Use Horner's rule of pre-compute values of alpha x to implement this hash computation efficiently as discussed here. This hash function has nifty property that so hash code of successive m character windows of a string can be computed in constant time instead of OM. Okay. Regardless of which hash function you decide to use, print statistics on the distribution of keys per bucket to see how uniformly. Odds are the first hash function you try will not prove to be the best. Watching up the hash function is an excellent way to slow down any application. Okay. B trees and all implementations. Okay. So modern programming languages provide libraries offering complete and efficient container implementation. The C++ standard template library is now provided with most compilers and available with documentation. Okay. The Leda 6 provides an extremely complete collection of dictionary data structures in C++, including hashing, perfect hashing, B trees, red black trees, random search trees, skip list. Experiments reported in here identified hashing is the best. Hashing is the best dictionary choice with skip lists and 2 to 4 trees. A special case of B trees. That's the most efficient tree-like data structure. Java collections. Okay. Notes. Is that all? Don't you do anything? Priority queues. Okay, so we just discuss. Okay. Page 79. I think it was page 79, right? Page 423, this page. So, insertion deletion from a hash into insertion and applications. Okay, open addressing, collisions in a hash table. So give me a ticket. Let me go open addressing. Here is open addressing. How do I deal with collisions? Open addressing, and that is all. Addressing search. I want to search in the whole. Okay, it found something. Okay, it is looking. Okay, there we go. Optimizing hash table performance is surprisingly complicated for such conceptually simple data structure. The importance of short runs in open addressing has to. Okay, how can I trees and other dictionary structures? This is what, page number 99. Is there open addressing? Okay, deletion in open addressing scheme. Collision resolution by open addressing. Collision resolution by chaining. Okay, so open addressing is marking that these are collision resolution by open addressing. Okay, collision resolution. No matter how good a hash function is, okay, hashing. No matter how good a hash function is, we had better be prepared for collisions, because two distinct keys will occasionally hash to same value. Chaining is the easiest approach to collision resolution. Represent the hash table as an array of m linked lists. I think I'm getting the idea. Right, I have load factor, I have size, or should I say capacity. Okay, it will still work since these values are not being used anywhere. All right. So I can save workspace as I'll just write hash maps and I can just go close project. Right. So we'll call it a day and okay, maybe I can still go. Right. Okay. No matter how good a hash function is, we had better be prepared for collisions because two distinct keys will occasionally hash the same value. Chaining is the easiest approach to collision resolution. Represent the hash table as an array of m linked lists. The ith list will contain all the items that hash to value ia. Okay. Thus, search, insertion, and deletion reduce to the corresponding problem with in linked list. If the n keys are distributed uniformly in a table, each list will roughly contain n over m elements. Okay, n keys and m. What is m? Represent the table as an array of m linked lists. Okay, n keys are distributed uniformly in a table. Each list will roughly contain n over m elements, making them a constant size when m is almost equal to n. Okay. Chaining is very natural but devotes a considerable amount of memory to pointers. This is space that could be used to make the table larger and hence the lists smaller. The alternative is something called open addressing. The hash table is maintained as an array of elements, not buckets. Array of elements. Oh. Each initialized to null as shown in figure here. On an insertion, we check if the desired position is empty. If so, we insert it. If not, we must find some other place to insert it. The simplest possibility, called sequential probing, inserts an item in the next open spot in the table. Okay. If the table is not too full, the contiguous runs of items should be fairly small. Hence, this location should only be a few slots from its intended position. Searching for a given key now involves going to the appropriate hash value and checking to see if the item there is the one we want. If so, return it. Otherwise, we must keep checking through the length of the run. Okay. Deletion in an open addressing scheme can get ugly, since removing one element might break a chain of instructions, making some elements inaccessible. We have no alternative but to reinsert all the items in the run following the new hole. Chaining and open addressing both require O of m to initialize the m element hash table to null elements prior to the insertion prior to the first insertion. Traversing all the elements in the table takes O n plus n time for chaining. Because we have to scan all m buckets looking for elements even if the actual number of inserted items is small. This reduces the O of m time for open addressing since n must be at most m. Okay, and now traversing all the elements in a table takes O n plus m time for chaining because we have to scan all m buckets looking for elements even if the actual number of inserted items is small. Right. That is correct. Okay. Here's the actual number of, but we use the hash function to find the actual number of inserted items is small. This reduces to O of m time for open addressing since n must be at most m. Okay. This reduces to O of m time for open addressing since n must be at most M. When using chaining with doubly linked lists to resolve collisions in M element hash table, the dictionary operations for n items can be implemented in the following expected worst case time. Okay. Search of n. Successor, predecessor, maximum, minimum. Worst cases of n over m. Resolve. Pragmatically, a hash table is often the best data structure to maintain a dictionary. The applications of hashing go far beyond dictionaries, however, as we will see below. Oh, substring pattern matching. Right, okay. So, I guess what we can do is of this project. This is hash maps. Yes, okay. So I have this hash maps. I have size. Still same. Threshold. The threshold resizing is called calculated as capacity times load factor. Okay, for example, inserting entries. When you add, it checks the current size exceeds the threshold. Current size, the number of entries. Okay, let me check this book too. Preliminaries, performance, okay. Cracking moisture, algorithms, data structures, structuring data, writing correct programs, a small matter of programming. From pseudocode to C, we have performance, using space, product, sorting, sample problem, searching heaps, string of pearls, sorting. Okay, this is a fairly dual linear binary structure for integers, heaps, sorting of pearls. Okay, I want hash. Let me just search hash. Hash table. Along with hashing program. Bins can be viewed as kind of hashing. What is this? Structure for integers. And then this is hashing, reading hash table by string of. This is searching. Okay. A real searching problem for the reading. What is bins bit factor? And bins can be viewed as a kind of hashing. Not. Okay, back of the envelope analysis showed the importance of keeping a dictionary in main memory. This was hashing this 60 discards 60% of the bits that remain. Data compression halves it again. The first hashing method uses an hash table roughly the size of the list and a hash function that maps a string into an integer in the range. Thus, we'll see a hash function of string. The ith entry of the table points to a linked list containing all strings that hash to I. Okay, so if null lists are represented by empty cells and the hash function yields to list 1, etc., then a 5-element table might look like list of a list of 5 words. Okay. To look up the word W, we perform a sequential search in the list pointed by the edge of W itself. The next scheme uses a much larger table. Choosing n equals 23 makes it likely that most cells contains just one element. This example, A is 13 and whole list is 5. Okay. Then we have the spell program, and the spell program uses n to the n equals 2 to the power 34 million, and all but a few of the non-empty list contains a single element. The next step is daring. Instead of a linked list of words, McCroy stores a single bit in each table entry. This reduces space dramatically but introduces errors. Uses same. Okay. Valid McCroy's spell. Okay. Let's see. Map, right? Okay. So I am on map. Okay, this is a std map. Okay, it's a hash. Okay, we can reduce the process. What page number is this? 162. We can reduce the processing time by building our own hash table using nodes that contain the pointer to a word, a count of how often the word has been seen. Okay, and a pointer to the next node in the table. Here's the hash table after inserting the strings in. This is the counter of how often this has been searched. Okay, we'll implement the hash table with this C structure. Okay, I have an array of words, an account, and a pointer to next. Okay. Even by a loose definition of word, the Bible has only distinct words. We'll follow the old lore of using a prime number near that for a hash table size, and the popular multiplier of 31. Okay, multiplier, I don't understand what is multiplier. A hash function maps the strings to a positive number less than n hash. Okay, these are the number of buckets. Okay, and okay, multiplier to compute the hash. Okay, this computes the hash. C++ until value of p is not null. Okay, that's a clever way to do that. Using unsigned integers ensures h remains positive. The main function initializes every bin to null. Okay, so I have for I equals 0 to n hash bin equals null, while the hash table and to write unsorted words and counts. Okay, word buff for I 0 to for p equals bin not null p next print p word prevent. Okay. The work is done by increase word, which increments the count associated with the input word and initializes it if it is not already there. Okay, so we have hash function, right? This is the hash function, right? Okay, hash. Okay, then we have for p bin not null, we copy str compare s and word is 0, then we increment it, and then we say p equals size of hash node, p count is 1. Okay, the for loop looks at every node with the same hash value. If the word is found, its count is incremented and the function returns. Okay, if the word is not found, the function makes a whole new node, allocates its space and copy string. Experienced C programmers would use str duplicate for the task, and inserts inserts the node at the front of the list. The C program takes about 2.4 seconds to read its input, the same as C++ version, but only 0.5 seconds for the insertions, down 4.9. There's 0.006 seconds to write the output, down. Okay. The complete run is 3 seconds, down from 7.6. The processing time is 0.55 seconds, down from 5.2. A custom made hash table in 30 lines of C is an order of magnitude faster than maps from C++ standard embedded library. Ah. This little exercise illustrates the two main ways to represent sets of words. Balanced search trees operate on strings as individual objects. These structures are used in most implementation of STL, set and maps. They always keep the elements in sorted order so they can efficiently perform operations such as finding a predecessor or reporting the element in order. Hashing, on the other hand, peeks inside the characters to compute a hash function and then scatters key across a big table. It is very fast on average, but it does not offer the worst case performance guarantees of balanced trees or support operations of other. Okay. Okay, using a hash table. Uh, hashing. Hash function. Your problems. How could you use hashing to speed up Markov program? Hashing. Hash values, algorithms, custom built hash table. Also appendix. Okay, now I'm on the appendix. Okay, fine. So, we'll continue next time.